But before I hand it over to John and Madison, I just wanted to welcome everyone to day one of Affordable Housing Week. And I'm going to, in the chat, put the URL for Affordable Housing Week and just make sure that you're checking out all the events throughout the week. And I want to say a special thank you to HTC member Ecotope and to Jonathan Heller and Madison Johnson, who are going to be presenting today on the Bayview Tower. I'm really excited to hear more about the heat pump water heating system. So I'm going to hand it over to John and Madison, and you can kind of walk us through the agenda and look forward to the presentation. Thanks.
Okay, thanks, Lauren. Hello, everybody. When we were asked to do something for Affordable Housing Week, we realized that we had just put this presentation together for the Efficiency Exchange conference down in Portland last week. That's Bonneville Power and Northwest Energy Efficiency Alliance annual conference. And so we're repurposing that presentation for today. The project we're talking about is the Bayview Tower apartments in downtown Seattle. It's a high-rise senior housing building owned by Seattle Housing Authority, fully occupied. And Seattle Housing Authority was interested in improving the efficiency at that building. They had an existing electric resistance water heating system, and Seattle Office of Housing stepped up to help fund a replacement with a commercial heat pump water heater system. And so this building represents a lot of firsts. It's the first US installation of Mitsubishi's commercial heat pump water heater solution, which is uses CO2 as a refrigerant. So it's also the first multifamily building with a commercial heat pump water heater designed specifically for domestic hot water in the US. And the delivery mechanism there is also a first in that we fully pre-packaged the water heating system in a factory off-site and delivered it on the back of the truck and hoisted it into place. And that allowed us to switch over from the old water heating system to the new with just a few hours of downtime. So with a fully occupied building, it allowed for this type of retrofit. So we are going to we'll talk some about that, what allowed for that to happen, and more about the building. And then we'll also talk about something that is another first for this project, which is demonstration of a commercial water heating system of this scale being used as a resource for the grid. So we've designed it in such a way that we're able to decide when the system operates and to shift the operation of the heat pump from the peak grid demand periods. And this is going to be something that's going to be increasingly important to utilities as we decarbonize the grid and start to rely more and more on solar and wind, because when we only get solar generation when the sun is shining, we only get wind when the wind is blowing, but people want to use hot water every day. And so our ability to decide when we run that equipment becomes super important with a decarbonized grid. So I just told you the whole presentation in the intro, but now we're going to do it with a little more detail. Yeah, I think that's. And Lauren, give me a thumbs up if you see our screen. Okay, great. So as I said, this presentation was originally for Efficiency Exchange, and I'm going to be presenting the engineering aspects of it, and then Madison Johnson, who's sitting right next to me, is going to be presenting the data analysis and lessons learned. Let's see if we can figure out how to use. Maybe we need to share a different screen. I'm trying to remember what my first slide. So as a quick introduction to Ecotope, for those of you who might not know us, we are a mission-driven company focused on leading the transformation of the building industry to a decarbonized future. And we have a research team as well as a design and engineering team that were both teams involved in this project. And we've organized the way that we think about our work in around 3 responses that we feel like the building industry needs to make towards climate change. The first, with this intentionally inflammatory photo that I've got here of a building after a gas explosion, is that we need to stop burning fossil fuels in buildings and move towards newer developing heat pump technologies instead, and electrify our buildings. Energy efficiency is still going to be primary. That's what Ecotope's been doing for 40 years. We need to use electricity as efficiently as possible because we're trying to bring our transportation system onto the electric grid, and we're trying to bring all of our heating onto the electric grid. And so we need to make room for that by doing that super efficiently. And finally, I alluded to it earlier, but as we decarbonize the grid, when we use electricity starts to matter as much as how much we use, because the electric grid has to be able to supply the demand at all time periods. So when really starts to matter, when we use electricity really starts to matter, and that's something in the coming up in the future. And so this project at Bayview Tower really brings together all 3 of those responses to the climate crisis by replacing the water heating system, because it's an example of electrification of water heating. It's a super efficient way to do that, and it allows us to shift the time of when we use that electricity off of the grid peak periods. And so our Ecotope's vision of what we're doing here with water heating is really transforming the water heating industry so that heat pumps become standard practice instead of gas or electric resistance, that we're getting system COPs of 3 or better, that we're using low global warming potential refrigerants in those heat pumps, that they're delivered in a plug and play fashion so that there's very little specialized knowledge and experience that's needed on the part of the designers and installers, that they're affordable, that they're reliable, and that they have the ability to load shift. And we see this happening over the course of the next 5 to 10 years. This is a rapidly developing market, both at the residential scale and the larger multifamily commercial scale. We've been working on these products for about 12 years, mostly funded by the Bonneville Power Administration's Emerging Energy Efficient Technologies program. And we've developed this understanding of what's really needed to bring a new technology from an idea or a prototype to the marketplace. And if you do these steps in order, it saves a lot of heartache and frustration, which we've experienced over the last several years trying to skip any of these steps. So it starts with a feasibility study, which is kind of an engineering due diligence study on paper, try to figure out where this technology might fail in the marketplace and address those before you try to bring it into a demonstration. And then also before you do a demonstration, we're starting with a heat pump technology, but there's a lot more to making a heat pump work in a building than just a good, well-designed heat pump. It's really part of an overall system that includes the storage tanks, the controls, the tempering valve, it's really a fully engineered system that has to be developed. So we go through a process of applications testing to make sure that all the other parts and pieces that are required to make the system work are integrated with that heat pump product before we bring it out to a demonstration. And this project at Bayview is the first demonstration of that Mitsubishi Heat 2.0 commercial heat pump water heater product. And as we do that demonstration, we're doing detailed measurement and verification of the performance of that so that we can provide feedback back to the manufacturer so that we can validate our estimates of how well this thing is going to work in the field and learn how to make that product better to roll it out into the marketplace. And this type of approach that we've been developing is really requires a lot of different partners. For this project in particular, I want to highlight Seattle Office of Housing, Seattle Housing Authority, Bonneville Power Administration, Mitsubishi, Steffes, who is the company that pre-packaged the heat pump. Did I leave anybody out? NIA, DNR International, Seattle City Light, a lot of partners. So this project, the goals of the project were to deliver reliable hot water with really minimal disruption to the tenants. They shouldn't really have known that their water heating system was being replaced, other than some feel-good announcements about the fact that it's using a third as much energy as it used to. We wanted to verify the performance of the Heat 2.0 product, and we were shooting for an average annual system COP of about 3. We wanted to identify opportunities to deliver and improve on a fully packaged system approach and demonstrate that. And then we wanted to test and demonstrate our ability to shift the load of this equipment off of utility peaks. And the results, it's been delivering reliable hot water for about 1.5 years, going on 2 years. We're not getting quite as good of a system COP as we were targeting. We're getting about a 2.3, although we've identified ways that Mitsubishi can improve the control of their heat exchanger assembly to get closer to that target of COP of 3. We demonstrated a successful installation of a fully packaged system, and we've shown the opportunities for load shifting and what we can get out of that Madison will show more details of. So the system design itself is it's essentially set up in a standard what we call a swing tank approach, which is the heat pump used to heat primary storage upstream of a temperature maintenance tank, and that temperature maintenance tank is getting the recirculated hot water and maintaining the water hot in the building so that it's delivered to the tenants quickly at temperature. And the difference of the Mitsubishi product to most of the products that are on the market right now is that secondary heat exchanger, so that the potable water is not going directly through the heat pump, but it's separated by a heat exchanger, which allows Mitsubishi to protect their coil from any water quality issues, scaling, and also allows them to put some freeze protect chemicals in that loop if needed. We didn't do that in the city of Seattle, but in colder climates, they may do that. And that secondary heat exchanger is actually the control of that is what's leading to our slightly under target performance, because the controls of that heat exchanger have to be just right to get as cold of water possible going to the heat pump. And Madison will show some of the data that allowed us to figure that out and provide some feedback to Mitsubishi for product improvement. And then the other thing I wanted to mention is that in this project, we were limited on the amount of storage that we could add in the primary storage tanks because of structural considerations for the roof that we put this on. So it's actually slightly undersized from what we normally would have or what we initially wanted to install in this building. And so our ability to do the load shifting is really, this is kind of a worst case scenario, and we're still able to do quite a bit of load shifting with what is otherwise a potentially slightly undersized heat pump and storage system. Specific considerations of the site, we had plenty of electrical capacity because we were starting with an electric resistance water heating system, so we didn't have to upgrade any panels or infrastructure to make that happen. We wanted to be careful about adding any unwanted sound from the compressors. So we thought about where we installed this thing to not impact windows or the neighbors. We decided to put this up on a low roof to get it up off the ground and out of potential harm from trucks backing up in the alleyway or vandalism. But because we did that, we needed a structural engineer and some additional support for the roof that we put it on. This is what the fully pre-packaged system looks like. On the far right there is kind of an exploded view of what's inside the skid. It includes the heat pump, the primary storage tanks, expansion tank, heat exchanger and pump assembly, controls and all the valving. And in the center there is a picture of what this first iteration looked like that was delivered to this building. It's kind of almost like a little pre-manufactured mechanical room adjacent to the heat pump. And then on the far left is kind of where Steffes is evolving the design in the future, more of a little smaller footprint and more optimized, more optimized footprint. So here's some photos of the heat pump system arriving on the back of the truck and being lifted into place. Doing it this way, we think has some real potential benefits for market transformation, in that by fully pre-packaging it, the installer really didn't have to know anything about how this heat pump system works. It comes as a widget. You connect the electrical power, you connect the cold water going into it, and connect the hot water coming out of it to the building. It really speeds up what's happening on site. It gets built the same way every time and pre-tested before going to the site. So really has the potential to save time, money, headache, and improve reliability. The other thing I would say about it is that by coming together as a single package system, you now have one place to go for warranty issues. Everything was supplied by the same person, instead of a mechanical engineer specifying the heat pumps from one source, the tanks from another source, potentially the control system from another source, putting it all together on site, or a contractor puts it together on site based on the engineer's design, and then some maintenance person comes and decides that a valve should be in a different position. It's like there's a lot of ways that site-built systems can go wrong that this addresses, so significantly reduces the risk of this type of new technology. So this is a picture of a typical hot water load shape for a multifamily building, at least pre-COVID. There's typically a large peak in the morning that's associated with people getting up and taking showers and making breakfast and coffee and so forth. Typically a low amount of demand in the middle of the day, because that's just the people that are staying home. And then a second peak in the evening around dinner time. And this is extremely inconvenient for the utility because that's exactly the shape of the utility peak demands. There's a morning peak in cold weather climates associated with morning warm up, people getting up and turning on their heating systems. And then there's an evening peak associated with cooling equipment coming on in the afternoon. So we would like to instead operate electric heat pump systems so that they run overnight when perhaps the wind is blowing and not a lot of people are using electricity. They run during the middle of the day when the sun is out and solar power is being generated, and that they're not running during those times when everybody else wants electricity, during that peak cooling time and peak morning warm-up time. So at Bayview, we tried to demonstrate to see how much time during that morning peak could we shut the system off and shut it off in the evening and still deliver consistent hot water. One thing that made that a little bit more challenging is that Bayview senior housing doesn't look, the load shape of the hot water usage is not the same as a typical worker housing building, which is that shown on the left there with the big morning peak and a secondary evening peak. The senior housing, since nobody's going anywhere, people get up at different times and they use their water more. There's more water use in the middle of the day. This makes it easier to shift usage out of that morning peak time, but makes it harder to shift out of the second evening peak because it's harder to catch up with your storage. The EcoSizer is a free online tool that Ecotope created with support from a couple of California utilities primarily, as well as from NIA, but from Southern Cal Edison and Sacramento Municipal Utility District. And this is a program that allows for optimizing the sizing of the heat pumps so that the heat pumps run for 16 hours a day or 16 to 20 hours a day, and the storage is sized so that it can carry the buildings through those peak demand periods instead of relying on quick recovery, which is what most gas systems have been designed around. The gas system has a relatively small amount of hot water storage and relatively big gas burner so that it can recover that really quickly. The more cost-effective way to do heat pump systems is a large amount of storage that enables you to coast through those peak periods and relatively small heat pump capacity. So we have a pretty simple and I would say somewhat ingenious way to manipulate the controls for these heat pumps to allow for load shifting. Under normal operations, there's an aquastat about 40% of the way up the primary storage tank, and the cold water floods into the bottom of the tank, and when it gets up to about 40% of the way up the tank, that aquastat sees that there's cold water and it says, okay, better recover, and it sends a signal to the heat pump to turn on. And then it recovers that bottom 40% of the tank. And so it has a pretty long compressor cycle, which compressors like to do. They don't like to turn on and off a lot. And so what we did with in cooperation with Mitsubishi is instead of using a single aquastat location to turn their heat pump on and off, we put 5 aquastats at various levels in the tanks. And then before those peak demand periods, those shed periods when we want to shed load, we, instead of looking at that temperature sensor that's 40% of the way up the tank, we look at the one that's way down at the bottom. And that forces the heat pump to come on much sooner and charge the tank all the way up before we enter that shed period. And we wouldn't want to do this all the time, like run the heat pump with a temperature sensor all the way at the bottom of the tank, because it would lead to these short compressor cycles. It would cycle the heat pump on and off a lot. But we want to just do that just before in the period of time before the shed, so that we know that we enter that shed period with a fully charged thermal storage battery. And then during that shed period, when we would rather the heat pump doesn't turn on, we're using an aquastat way at the top of the tank, so that it allows the whole bottom of the tank to get drained down. We don't let it drain all the way because we don't want people to run out of hot water. So we turn it on if that cold water level gets up towards about 85% of the tank. And then we turn it on to recover down to about that 40% level, and then we'll let it come back on again if it needs to cycle during that shed time. Am I turning this over to you now?
Yes.
Yes. Okay. So that's the kind of engineering system introduction, and now I'm going to let Madison talk about the monitoring that we did and the testing of the load shift controls and what we learned about that.
Hi, everyone. So as John mentioned, we just went to the Efficiency Exchange in Portland, where we got to hear from utility companies all over the Pacific Northwest and hear about their needs as we electrify the grid. So utility companies need to be able to meet consumer demand even during these periods of peak use. So one of our goals of load shifting is to alleviate stress on the grid during periods of peak demand. And we want to do this by utilizing that thermal storage tank, which can be charged up during our load up period and allow the heat pump to remain off during peak hours, which is when we schedule our shed periods. At Bayview, we have around 70 monitoring points that we're collecting data on every single minute. So we can look at the system in really fine detail. So I'm going to show a little bit of our M&V data. This is how we evaluate load shift performance, how we see how the system is performing overall, and also how we can identify areas for system improvements. And so this particular day is from May 2022, where we saw some ideal system behavior that we want to be able to replicate all year long and in other buildings. This behavior is pretty representative of what we saw over the summer. And the first thing I want to draw your attention to is the background colors of the plots. These indicate the control sequences that were sent to the heat pump. So we have blue for load up. This is when we're charging up the tank, and then green for shed when we are trying to keep the heat pump off. So on this particular control sequence, we have a load up period from 5 to 6 a.m., followed by a 3-hour shed from 6 to 9 a.m. with a little bit of a break, and then we begin loading up at noon for our evening shed period, where we shed again from 6 to 9 p.m. And so the first data point we'll look at is available hot water storage in our primary storage tanks. The storage tanks at Bayview, there are 3 of them, and they each have 5 temperature sensors. So using this, we're able to get a snapshot of the tank's temperature profile at any point in time, which allows us to determine how much available hot water we have for the building. Our storage tanks are around 850 gallons, but we're storing the water around 150 degrees and then mixing that with cooler water to supply it to the building at 120 degrees. So we're actually able to store around 1,200 gallons of hot water in those storage tanks. And so here, one important thing to note is that as we enter our shed period right after loading up, we reach a maximum in our hot water storage. And then as we exit the shed period, we reach a minimum. And so this means as soon as our shed period is over, we're immediately starting to generate more hot water. You may notice that as we enter the morning shed period, we reach around 1,100 gallons of hot water in our storage tanks. But as we enter the evening shed period, we don't quite reach the same levels. There's two reasons for this. Reason number one is that at 5 a.m. when we're loading up the tank, not very many people are awake at that hour using hot water. And so the system isn't having to compete with much hot water use. Whereas in the afternoon, especially at Bayview, there are tenants in the building using hot water. And so in the afternoon, the system is not only having to keep up with the hot water usage, but also generate additional hot water to charge up our tanks. And then the second reason is that overnight, our storage levels remain moderately high. And so in the morning, it's not having to make up as much storage. Whereas in the afternoon, we are having to recover from nearly depleting our tanks in the morning shed period. So the system has a little more work to do. And so one important finding from this is that having adequate storage is very important to load shifting, but it's also really important to have enough capacity if you want to complete 2 shed periods per day.
Which I'll point out that most projects will only attempt to do 1 shed period per day. We're really stressing this system to see if we can do both.
And then the next data point we'll look at is power into our primary heat pump. So the goal here is to have 0 power input during the entire shed period. You will see some oscillations here. That just indicates the heat pump is on, and then if we're flatlining at 0, that indicates the heat pump is off. So as we enter our morning load up period, the system was previously off, and this is because the system had adequate hot water storage. So John mentioned earlier that there are special temperature sensors called aquastats in the tank. And so when the heat pump was in normal operation, there was hot water at that aquastat, and the system had adequate hot water storage. But as we enter the load up period, we change locations of that aquastat sensor, and the heat pump is triggered to turn on and load up the storage tanks. And then as we enter our shed period, that aquastat location moves in the opposite direction, and we're able to coast through the shed period without turning on the heat pump. And then as we exit the shed period, that aquastat is moved back to the original location, and the system is triggered back on. And so this was a really successful day because we were able to keep the heat pump off the entire time for both shed periods. And this is pretty representative of what we were able to do over the summer, especially. Next variable we'll look at is power into the swing tank. The swing tank is used for temperature maintenance heating. And we did choose to use the existing electric resistance equipment at Bayview. And so we'll talk a little bit later about what this means for the energy use profile when it comes to temperature maintenance heating. And then another variable that we often look at is the hot water usage from the tenants. Notice here that we have our peak during the early afternoon. So around 12 p.m. is when tenants are using the most hot water, which, as we mentioned earlier, does make it challenging to do that second load up period. But here you can see that despite that, we were still successful in load shifting. And then another data point that's really important to evaluating performance is the temperature of the water that's exiting our primary storage tanks. This just helps us verify that despite doing these scheduled off periods, we're still having hot water exiting the storage tanks. So despite this long period of off time, our water coming out of the storage tanks is still between 140 and 160 degrees. This water will be mixed with some cooler water through a mixing valve and delivered to the tenants at 120 degree to 125 degree range. And then lastly, some important points at Bayview are the inlet and outlet water temperatures of the heat pump. Systems like the Mitsubishi QAHV require large temperature differences between the inlet and outlet water temperatures. So if we see inlet water temperatures that are too high, it does impact the system's capacity and its COP. And so you can see we have a range of around 80 to 120 degrees, and that's a little bit higher than we would like to see. So this did have an impact on system performance, but it's something that we've been working with Mitsubishi on. And that's one of the exciting things about this project, is because we're looking at the system in such detail, we can find things like this and work with manufacturers to improve for future installations. And then lastly, I just want to point out that this flatlining that you're seeing just indicates the heat pump is off. This is just another way we can verify the heat pump has been off during this time. And so now that you've seen ideal system behavior and 2 successful shed periods, you might be wondering what happens if we're not able to complete an entire shed period. So this is an even more aggressive schedule that we attempted in October of 2022. We have 2 4-hour shed periods. So this is quite a long time to be attempting to keep the heat pump off. We did this because we kind of wanted to test the limits of our load shifting capabilities, knowing that we do have a backup electric resistance water heater. So the tenants are always going to be guaranteed access to hot water, even though we are stressing the system. So as we enter our morning shed period, we have around 800 gallons of available hot water stored up. And we do make it almost all the way through the shed period. You'll see that red line dips pretty low, and that triggers the system to turn on before the shed period is over. We do have a little bit of difficulty loading up on this particular day during the afternoon. Despite that, the system does still attempt a second shed period. However, we only make it about a third of the way through before the system does turn back on. And I think there's 3 main takeaways from this. Takeaway number 1 is that despite us not completing the entire shed period, we're still able to shift a significant portion of that energy use outside of the peak demand period, which is, we would consider pretty successful. The second takeaway would be that the system did have enough capacity to be able to handle the load. We didn't require any backup electric resistance heating here, and the system was able to recover from this partial shed period. However, we could have used a little bit more capacity to be able to load up for that second shed period. And then the third takeaway, and arguably the most important, is that despite our stress on the system, we were always guaranteeing the tenants access to hot water. So there was no disruption to them through this experimentation. And so this is an hourly energy use profile at Bayview, and it kind of shows 2 of Ecotope's guiding principles in action. Number 1 is that efficiency is energy. So if we compare the green electric pre-retrofit electric resistance usage to the blue post QAHV install, you can see that the QAHV is much more efficient, and it uses less energy during every hour of the day. And then the second guiding principle in action here is that when matters. So we have 2 peak periods, one in the morning and one in the evening, where we've been able to shift all of the most of the energy outside of these peak periods, and you can see that in the red line. We've pushed that energy outside those peak demand periods. And then this plot shows some similar results. We have it separated by a morning peak period and an evening peak period. Pre-retrofit, using the electric resistance system, we used around 75 kilowatt hours of energy per peak period. With the QAHV, we use significantly less energy, and then when we load shift with the QAHV, we can reduce that to just a handful of kilowatt hours per peak period. And then I want to talk a little bit about electric resistance use. So our swing tank system, which has the electric resistance elements, is used for temperature maintenance heating. And so there's 2 cases in which this temperature maintenance system will turn on. One is due to recirculation losses, and this just means when tenants aren't using very much hot water, the water that's circulating the building begins to cool, and so our swim tank will turn on and heat that water back up to set point. The second situation is in extreme cases, the electric resistance system can be used for backup heating. This would occur if we were to completely deplete our hot water storage tanks and the heat pump was not able to handle the load on its own. The majority of electric resistance heating that we saw at Bayview could be attributed to recirculation heating. We only observed this backup heating on extreme winter days when the system entered defrost mode for the majority of the day. And we can use our monitoring points to verify why the electric resistance turned on. So if we can see that that we have adequate hot water storage levels and that the temperature coming out of the primary storage tank is adequately hot, we know that this electric resistance heating is used for recirc. And because we used the existing equipment, we didn't have controls implemented to be able to load shift with the temperature maintenance system. So John is going to talk a little bit about how we can load shift the temperature maintenance system on future sites. And I do have some summary results that I wanted to share. So basically what we did for this project is our team would sit down and determine a control sequence that we'd like to implement for 1 to 2 months. And we'd evaluate how the system did, and we might change the schedule accordingly and see what findings we wanted to discover. And so our first control period from May through June, we attempted 2 3-hour shed periods, and we were able to keep the system off 91% of the time that we had scheduled off. We were even more successful in the second control period, which was from June through July. It was again 2 3-hour shed periods, and we kept the system off for 98% of the scheduled time. And that 2% is usually just due to a little bit of a lag in the system, like maybe it turned off a minute after it was supposed to. So this was really successful. You'll notice we do drop off a little bit in the fall at 85%. However, we did attempt a much more aggressive schedule. So instead of 2 3-hour shed periods, we were doing 2 4-hour shed periods. So this 85% we actually considered really successful. As we enter the winter, we still attempted 2 4-hour shed periods. And this is even more ambitious because heat pumps draw out heat from the surrounding air. And so during the winter, they do experience a little bit of a capacity derating. And so this was a very ambitious schedule to attempt. And we did identify quite a few areas for improvement that will help us improve these numbers on future installations. So I'm going to hand it back over to John, where you can talk about some of those areas for improvement that we identified.
Okay, and I'm going to try to go quick so I leave a little bit of time for questions if there are any. So some of the lessons learned. One interesting one is that you have to take into consideration when sizing these Mitsubishi products that 20% of the time during the worst case hours when it's humid and cold outside in December, it's going to be in defrost and not making hot water. So systems need to be about 20% bigger in our climate to account for that defrost time. The problems that we identified getting cold water on the other side of the heat exchanger into the heat pump have been fed back to Mitsubishi, and they're working on pre-packaging the heat exchanger control and pump assembly into that device that you see in the middle on the slide as a pre-manufactured piece that will help optimize that pumping and temperature management to get COPs above about 3 is what we think we can do with that once Mitsubishi completes their manufacturing of that. We have some design changes that we think could be made to allow us to not only shift the operation of the heat pump, but shift the operation of the temperature maintenance system as well, which we're calling a pumped swing tank. And so that, particularly in new construction at Bayview, we wanted to reuse as much of the existing equipment as possible, so that we probably wouldn't use this at a Bayview type retrofit, but for new construction, we think there are design ways to control that swing tank as well. And what we kind of see in the future is that as we get better integration with the utility, knowing what the most likely scenario is that more and more utilities are going to start charging time of use pricing for electricity. So electricity on those peak periods will be really expensive, and electricity when there's a surplus of solar will be cheaper. And so if we had that time of use pricing picture a day ahead, and we know what the load shape is in the building, we could write an algorithm that could optimize when those load up periods are and when the shed periods are to keep the operation of the equipment as inexpensive as possible for the owner. So the last thing I'll point out is there's a QR code here that, or the web address at the bottom, that will take you to a 3D virtual tour of the Bayview project. And this was created with funding from Bonneville Power Administration, joint project with Ecotope and DNR International. And there's interviews with Seattle City Light, with Ecotope designers, with Mitsubishi, and you can go inside the skid system and click on the different parts and pieces of the system and learn more about how they're sized, how they're controlled, what they are, and so forth. So if you've got a few minutes, I recommend you take the virtual tour of the Bayview project. So with that, we end our scheduled presentation and open it up to questions.
John and Madison, there's a question from Len in the chat. That if you have sufficient storage tank volume, could you do load shifting with a purely electric resistance system? Yes,
yeah, you could. It'd just be dependent on how that system is sized. And utilities are doing some pilot projects with electric resistance residential tanks, trying to shift operation out of those peak periods. But so yeah, theoretically it could be done with electric resistance as well.
Looks like there's a question from Kevin. Can you locate the outdoor unit in a location less proven or less
exposed to?
Yes, exposed.
Yeah.
Thank you. To frosting over.
Yeah, certainly. We've done a lot of parking garage installations in the Seattle area, and that the first commercial heat pump water heater systems in Seattle that Ecotope did 10 years ago with Bonneville funding were all focused on below grade parking garages, because the equipment that was available on the market at that time was mostly using R134 refrigerant, which doesn't do very well below about 40 degrees. And so Ecotope recognized that parking garages stay around 50 degrees year round. And so we installed our first demonstration projects in those below grade parking garages to take advantage of all that earth contact. It's almost a ground source heat pump system because of all the concrete and earth contact down there. It's not as necessary with CO2, because CO2 functions quite well down to 0 degrees Fahrenheit. So in the Seattle climate, CO2 can be outdoors year round. We may get less frosting in a parking garage, which would allow you to downsize a little bit. So yes, long answer, sorry. Parking garage is a good idea if you have access to that.
Great. There's another question about whether there's any data on how jacket losses for the storage tank affect efficiency when loading the system.
You have an answer to that, or?
I don't.
So the system COP that we're reporting, that 2.3 that we're getting at Bayview, and the greater than 3 that we think we can get with the Mitsubishi product in a swing tank arrangement, that includes all of the energy going into the system, not just the heat pump, but also the electric resistance, temperature maintenance backup. So the storage tank jacket losses are part of those recirculation losses that have to be maintained and made up, and will impact the overall system efficiency. I will say that the jacket losses are the smallest component of that. Most of the energy that's lost is in that, mile of piping that's going all through the building to get close enough to all of the showers, so that you don't have to wait for water to get from the basement all the way up to your 10th floor apartment when you turn the shower on, if you're the first one up in the morning. So we keep that water circulating through a mile of pipe in these big buildings, and that's where almost all the losses are. The jacket losses at the storage tanks are relatively small. And that recirculation, that temperature maintenance energy typically represents about 30% of the energy use of a commercial hot water system in a multifamily building, because in multifamily, we have to keep it circulating all the time, because somebody way up on the top floor in the corner might want to take a shower at 3 a.m. And if we didn't have that water circulating, they would have to wait half an hour. They'd have to run their shower for half an hour to clear all the water out of the pipe between the basement and the top floor, and run all that water down the drain. So we can't really get away from circulating water all the time. What we can do is improve the layout of our piping in the building to make it as short as possible, to make the pipes as small as possible so they have as little surface area as possible, insulate them well, and not have any thermal bridging where they connect to the structure. So there is a bunch of work to be done to improve distribution design, and that does ultimately impact overall water heating energy use quite a bit.
Great. Any last questions in the few minutes that we have? And feel free to unmute yourself.
Yeah, just speak up if that's easier. And Lauren, are you going to share the presentation so people could find that URL?
Yeah, absolutely. So in the next couple of days, we'll have the recording for this presentation up on our Affordable Housing Week website. Let me put that back in the chat in case folks see it again. And we'll also have it up on our YouTube channel as well. So please feel free to share with your colleagues who weren't here today, or if you want to reference anything back. Ron does have one more question in the chat. Can you see that, John, or do you want me to read it?
Yeah. What would be the #1 tip for new construction for heat pump water heaters to meet the 2021 Washington Energy Code? I think there's a lot of potential for, well, okay, tip #1 would be pick a system that's on the qualified products list of the advanced water heating specification. So Northwest Energy Efficiency Alliance has an advanced water heating specification And as part of that, there's a list of qualified products. That means that the products have been, you're not just buying a heat pump, but you're buying a fully integrated, tested, demonstrated water heating system that includes the heat pump, the storage tanks, the control system, and the temperature maintenance system all integrated together. So yeah, tip number one is to look at that list. Advanced water heating specification, qualified products list for commercial products. Tip number two would be consider a fully prepackaged system, such as the one that was installed at Bayview, or the water drop manufactured by Small Planet Supply down in Lacey. They're packaging up the CO2 heat pump. So for a building with like 100 people or less, that CO2 product, the water, it's called the water drop, the fully prepackaged system, would be a great option.
Great. Well, what a wonderful presentation, John and Madison. Thank you so much for your time. Really appreciate it. Yeah, and it's always great to hear from you. Wonderful experts in the sector. So thanks everyone so much for joining, and please check out our calendar of events for the rest of the week, and hope you get to enjoy some sun today.
Yeah, thanks for listening, everybody.
Thank you.
Thank you.